So Eduardo, I see that you're actually scheduled for 3:55, but Ram, is it okay if he starts at 3:45 just so he can have more time for questions?
That's fine, Errol. We can start him now.
Okay, that sounds great. All right, Eduardo, are you ready?
Yeah, hi.
Okay, hi, please take it away.
Okay, so can everybody see my presentation now?
Yes.
Okay. Well, good afternoon to all the attendees at the ESI. I'm Eduardo González-Mora from the Sustainable Energy Systems Engineering Department at the University Autónoma del Estado de México. I'm going to present the maximum thermodynamic efficiency evaluation of a conceptual direct steam generation power plant. Okay, the contents of this presentation will be a brief introduction to Endoreversible model basis that is used to explain the determination of the case of study, the efficiency comparison, and the conclusion of the current analysis. Well, in the 19th century, the upper limit of heat engines was established by Carnot limit in the classical thermodynamics. This famous equation states that the maximum efficiency of a reversible heat engine is just a function of the quotient of the temperature of the heat reservoirs. However, the first correction of the model, called Endoreversible or finite-time thermodynamics, was postulated in the middle of the 20th century, first by Novikov and a little bit later by Coulson-Alborn. In these models, the maximum efficiency is somehow similar as the Carnot efficiency. Let's say that the quotient of the temperature heat reservoirs still appears, but now it is included in a square root. In this table, I've just included some power plants around the world, two of them in Mexico, that uses different heat sources in order to compare to the Carnot efficiency, the Coulson-Alborn efficiency, and the observed efficiency by means of the relative error. In the four cases, the Carnot efficiency overestimates the efficiency of the thermal power plants, while the Coulson-Alborn shows a more realistic value for the power plants. In this way, for example, the observed efficiency of Punta Prieta power plant located in Mexico that uses fuel oil presents a relative error of 8% using the Coulson-Alborn efficiency if we compare it to the 40% if the Carnot efficiency model is used. This immediately shows the advantage of using this corrected model, this Endoreversible thermodynamic model. The main difference between the classical thermodynamics model and the Endoreversible model is that in the last, for the quantification of the energy between the heat reservoirs, a conductance is taken into account. In other words, the finite size of the heat reservoir must be modeled. So dissipation of energy in the interface of the heat reservoir and the heat engine is now considered unquantified. However, the heat engine is still considered as reversible. On the other hand, if the heat engine consider the internal reversibilities by means of the turbine, for example, a good agreement between the models and the observed performances is shown, and it can be seen in the previous table. If we account as G for the thermal conductances, the work output is just a function of the square roots of the temperature and so the efficiency. On the left picture, a plot of the work versus efficiency is shown. Under this condition, an engine behaving as a fully reversible heat engine, in other words, a Carnot engine, will not deliver useful power, since the reversible heat transfer means an infinity slow transfer and consequently slow work power output. In other words, too much time to get useful power, which contradicts in essence the purpose of the heat engines. While a fuel Endoreversible model will achieve a maximum work output. Of course, while modeling an irreversible heat engine, the work output will decrease, but still presents a better agreement with the real power plants. On the right picture, a plot of the heat consumption and the entropy generation is shown. Again, the heat consumption and the entropy generation is 0 for a Carnot engine, whereas for an endoreversible engine, it must lie somewhere between, depending on the physical construction of the heat engine. Since I am going to model a steam Rankine power cycle, then the endoreversible model needs to be addressed. Again, we have the heat reservoirs, a heat source at high temperature TH, and a heat sink at low temperature TL. The high temperature of the heat engine TW and temperature TC are shown. These temperatures are due to the heat transfer over the frontiers of the heat reservoir with the heat engine. On the right, a schematic temperature entropy diagram for a conventional steam Rankine cycle is shown. And in this plot, the temperatures of the heat reservoirs are included to indicate precisely the heat transfer process QH and QL. For this situation, the endoreversible efficiency is almost equal to the Coulson-Arbon efficiency stated previously. However, now we need to take into consideration the highest temperature of the heat source, TH1, and the lowest temperature of the heat sink, TL1. Okay, now let's describe the case of a study. In this analysis will be done over a conceptual solar thermal power plant located in Agua Prieta, Mexico in the Northeast. The power output of the plant is of 10 megawatts, and instead of a conventional steam generator, a linear Fresnel reflector will be used in direct steam generation mode. This direct steam generation mode means that the high temperature and pressure steam is generated in the loop of the solar field instead of using a commercial working fluid, oil, for example, and a heat exchanger, as occurs in parabolic through collectors of commercial solar power plants. This leads to a higher efficiency of the whole plant since the solar radiation is converted almost directly to the steam. For this case, the Rankine cycle, I'm considering 2 and 3 steam extractions to compare the behavior of the system. As a fixing condition, the inlet temperature and pressure of the turbine are established as 400 centigrade and 100 bar, and 0.08 bar at the outlet of the turbine. Here I'm showing a schematic diagram for the 2 steam extraction, including the linear Fresnel reflector solar field, instead of the conventional boiler or the parabolic through collectors. And all the associated equipment of the cycle, the condensers, the pumps, the open and closed feed water heaters, and the throttling bolt. Since the temperature and pressure of the turbine inlet and outlet are fixed, a pressure extraction must be determined. The determination of the pressure steam extraction was under the assumption of minimum exergy destruction or minimum entropy generation to achieve a maximum efficiency of the whole cycle. As shown in the contour plot, there are some pressures that have no sense in the thermodynamic jargon. Let's say that the exergy destruction cannot be negative. But there are many pressures where there is positive, but just a few with a high efficiency. This condition is achieved around 7 bar. However, including all the equipment at 7 bar, the surfaces of the feed water preheated increased considerably. But at 8 bar, it seems to be a fair relation between high efficiency and a proper size of the feed water heater. Once this pressure is determined, it's possible to characterize all the states of the cycle as represented in the temperature entropy diagram. For the 10 megawatts output, 12.81 kilogram per second of steam are required, and the temperature for high and low condition in the heat engine are 672 and 496 Kelvin. For the three steam extraction, we have included another closed feed water heater. So now we are adding another degree of freedom that must be determined as has been done as in the case of the 2 steam extraction. Now in this case, the pressure extraction points are at 4 and 2 bars. Again, to get the 10 megawatts output, a flux of 13.26 kilogram per second are needed, and the temperatures for high and low condition in the heat engine are 672 and 485 Kelvin. Then the temperature and size of the heat reservoir must be determined. So an analysis over the linear Fresnel reflector must be carried out. The Fresnel reflector is conformed by a flat parallel rows of mirror that reflects the sun to a focal line. as shown on the left. In the focal zone, a secondary concentrator is placed to focus all the rays around the tube where water steam will be circulated. Note that at the lower part of the cavity formed by the secondary concentrator, a glass window is present in order to reduce the heat transfer loss of the receiver to the ambient. We have to characterize the thermal behavior of the linear reflector, so all the heat interaction are schematically shown on the left picture. And on the right side, I'm showing the heat transfer resistant model to define the direction of the heat fluxes. Each surface has a number to identify it. The number 1 is considering the water steam bulk temperature, 2 for the inner side of the tube, the number 3 for the outer part of the tube, number 4 for the reflector of the secondary concentrator, 5 is for the thermal insulator, 6 for the inner side of the window at the aperture, 7 for the outer, and 8 for the ambient. So in this model, we have 15 heat fluxes and 7 temperatures that must be determined. Once that the heat transfer model is solved, the temperature of the other side of the receiver can be plotted, and we can determine the length of the solar field. We can see in these pictures the increase in the temperature over the loop of the Fresnel reflector solar field for both cases, 2 and 3 stream extractions. Now that we have fully characteristic the cycles, we can calculate the efficiency. For the 2 stream extraction, the efficiency is 0.31, the Carnot efficiency is 0.57, and 0.38 for the Coulson argon. Similarly, for the 3 stream extraction, the efficiency is 0.315, 0.57 for the Carnot efficiency, and 0.34 for the Coulson argon. Since some irreversibilities were considering the heat engine, turbine and pumps, the efficiency of the whole plant is lower than the Coulson argon efficiency that I'm showing in the curves in red and in blue in the plot here. Now compare the efficiency of the Concepta power plant with the Punta Prieta power plant in Mexico too. We can say that the efficiency estimated and observed are fairly similar, and so the relative error with the Carnot efficiency and Coulson argon error. It can be seen that the Coulson argon present a more realistic upper limit, not only for conventional power plants, but also for the solar power plant here discussed. Finally, the conclusions is that we have shown that the Endoreversible thermodynamics model allows a more realistic analysis of concentrated solar power plants. This is important to address since in the solar engineering literature, this kind of analysis is done, but is not fully discussed. I mean, the determination of the size of the solar field is always determined, but the whole efficiency of the system is always compared to the Carnot efficiency. The 2 Rankine cycles were analyzed where a linear Fresnel reflector substitutes a conventional steam generator, and the optimization of the pressure extraction leads to a high efficiency quite similar to the Coulson argon. And finally, that the relative error to compare the maximum efficiency between the conceptual plan is minimized as shown. So this disagreement establishes a proper way to discuss the theoretical efficiency of the next generation solar power plant. But what's the most important point here? Well, we must address that the power generation was the first reason of the thermodynamic birth. The worst of all the thermodynamicists since the 19th century, almost in engineering, were focused on improved efficiency. Recently, the concentrated solar power has been witnessed an increase in deployment around the world. Let's say Spain, China, North Africa, USA, and Chile, just to mention a few. This increase is stressed by the urgent necessity of include renewable energies in the energy supply chain. However, the behavior, power output, and efficiency must be studied to make final decisions. These decisions obviously are technical, economical, and environmental that affect directly the social sector. Why? Well, it has been established that not only high efficiency stands for high power output, but also for low thermal pollution and a better use of the resources, even though they invade renewable resources. Understanding that thermodynamics is intimately related to the life of society allow us to establish a better concept of the rational use of energy. And that's all for my part.
Thank you so much. Do we have any questions for Eduardo?
I would like to ask a question, if I can.
Absolutely.
I don't quite understand the meaning of this corrected efficiency. It seems to be closer to the actual practical efficiency of the plant, but the Carnot efficiency places the true upper limit, which means there should be room to improve even on that efficiency. So what is the point of judging the plants against this lower efficiency?
There's not a real interest in determining a efficiency for this corrected model. I mean, the main part here is that in solar engineering, we are always dealing with determine the size of the solar field. So we are trying to do so by means of the Carnot limit. We are not dealing with the real surfaces or the real heat fluxes that the solar plant is showing, is behaving. So this kind of endoreversible model, besides of a more agreement with the theoretical power output, describes in a better way the length, in this case, of the solar thermal power plants. Of course, as you mentioned, the Carnot efficiency poses a limit that we are trying always to achieve. However, there's a vast literature almost that began in the 90s that state about trying to include this kind of analysis that is almost a step behind of non-equilibrium thermodynamics for solar power plants. It's been established that this kind of analysis has to be done. However, there's still a lack of information about that. So we are trying to get to that point, start and expand this kind of analysis to get a more realistic analysis for the power plants, in this case for solar power plants.
All right, thank you for that question. Do we have any other questions? There's still some time until the next session starts at 4:15.
I'm just curious, Eduardo, that like how many solar thermal plant are in Mexico? I see you have given so much example, but like in the overall energy chain, energy mix, how much is the contribution of that kind of thermal plant we are talking here?
In Mexico, we just have one solar power plant. It's not fully solar, it's a combined cycle. The solar collectors are used for preheating. But there are some interest by the government to include more renewable sources of energy. So we are taking this concept of direct steam generation because it's a cheaper way to produce this kind of steam for conventional steam Rankine power cycles. In Mexico, as I mentioned, we just have one solar power plant in a combined cycle. So this kind of, well, in fact, this analysis was proposed to establish future direction and implementation of this kind of technology in Mexico, principally in the Northeast, in the Northwest of Mexico.
Yeah, that's really great to know, because I can see that even in USA, I work for a renewable energy laboratory, and recently there has been a lot of interest in this kind of plants for various regions. Therefore, I was just curious, like, what's the status in Mexico compared to here? And good to know that.
Okay.
I think if we are done, then we can close the session, I guess, Gerald, and give some people break, and we'll convene back at like 4:15 for the next session, if you want.
Yeah, that sounds great.
Okay. With permission from Gerald, and we're gonna close this session, and we'll convene back here in this room at 4:15. Thank you so much.